Hello everyone. In the previous section you saw that charges may not come as points, and in fact charges never come as points, but they could be distributed over shapes. They could be distributed over a line, which we call linear charge. They could be distributed over a surface, which we call surface charge, and they could be distributed over a volume, which we call volume charge. So the next question which comes is, how can we calculate the electric field for these distributed charges? I'm going to make my example assuming volume charge, but wherever I put volume charge, the charge could be 9, and then the integral will have to be, instead of being a dV integral, it will be a dl integral, and if it was a surface, it would be a ds surface. So you can easily arbitrarily change these elements around. So let's assume that I have some arbitrary shape over which the charge is distributed. So there is some charge which is distributed here, and the charge is distributed in volume and has a volume charge density given by rho v. And I want to go to a point P here, and at that point P, I want to calculate electric field. If I asked you the question, there is charge Q1 present here, there's charge Q2 present here, tell me what the electric field at this point P will be, you would have just told me, you know what, let's just draw. There is electric field due to 1, there is electric field due to 2. We will do a vectorial sum of these of the electric fields due to the individual charges. What is this principle? This principle is superposition. It is basically saying that the electric field due to an individual charge doesn't get affected when I bring another charge into the system. That is the principle of superposition. Superposition holds here too. What do you do with integrals? In an integral, you take your shape and you break the shape into small pieces each, and then as you add these small pieces up, you get the shape back. So that's the same thing we can do here too. We can go to some arbitrary point in the shape. So we'll go to some arbitrary point A, and at that place, because charge is distributed over volume, at that place we would take a small differential volume dV. So the charge is distributed over a volume, we'll break this into small pieces. Each piece is extremely small, and within this piece, the charge density is rho v. So within this piece, I would have some charge which is like a baby charge, and that charge would simply be charge density multiplied by the volume. So this volume, we can treat it, because this is a differential element, very small, we can treat it like a point charge. And if we treat it like a point charge, we can then say that the electric field due to that point charge, or this small baby charge, is going to be a small baby electric field, and or a differential electric field, and the value of that differential electric field is going to be k dq by r. Let's call this distance r. The distance r I'm calling is from my arbitrary point on the charge to the point where I'm measuring P. P we will always call observation point. So this becomes, dE becomes k dq by r square. I'm treating dq like a point charge, so that becomes r square, and it is in the direction of line AP, which is this direction r hat. To calculate, let's say this is the electric field at point P. To calculate the total electric field at point P, what I have to do is I have to take this, move this around wherever charge is present and account for every single differential element over that charge and keep on adding things up. So I will get electric field, which would be now an integral, and since the charge is distributed over a volume, this would be a volume integral. And if you want to remind yourselves, volume is defined by 3 dimensions. So if you want, you can put 3 integrals just to remind yourselves that there would be some 3 dimensions to define this volume. And the value would be k dq r square r hat. What is this volume going to be? This volume is going to be the volume over which this charge is present. I have to go and I'll have to set up an integral over this term. This is how we can calculate electric field for distributed charges. If instead of the charge being in the volume, if it was on surface, all I have to do is put surface, and this would become dq would be rho v ds. If the charge was on a line, this becomes rho l dl. That's all I have to do. I can make the argument that way. Surface is volume with one dimension approaching 0. Line is volume with 2 dimensions approaching 0. So the argument remains the same. This integral is not straightforward at all. This is probably the worst thing you've done in your life yet. This integral is a vector integral. Not only as I go to different points, so let's say A was here, after I am moving in the integral, A goes to another point over here. Does the value of R change? Yes, that distance changes, but look at it. The value of electric field due to the differential charge here would be pointing in that direction. The value of electric field due to a differential charge somewhere else would be pointing in that direction. So not only do scalar quantities vary, the direction varies too. And you have to account for that. This addition which you are doing is a vector addition. Not a very, very straightforward thing. So you cannot just directly integrate this term over here. You will have to account for R hat terms. And the only way to be able to do that is to be able to break these electric fields. So we have DE, DEP. We will have to break this in DEX, DEY, and DEZ. You'll have to break it into 3 Cartesian coordinates. DEX, DEY, DEZ, and when you're integrating DEX, everything remains in x hat direction. So this is basically saying this is in x hat direction, this is in y hat direction, this is in z hat direction. When we are breaking it in x hat, everything remains in the same direction, so we can only do the scalar integral. When we do y hat, only everything remains in that y direction, so we can do this integral, and so forth. Same for z hat. But there is an issue here, and we will, what I'm saying right now will become clear as we do the examples. How do we choose the coordinate system? The coordinate system is going to be chosen based on the shape of the charge, how the charge is distributed. You have seen in first week that if You want to integrate over circles, polars help you. If you want to integrate over spheres, spherical coordinates help you. So the setup of this integral will depend upon the coordinate system you're using, and the coordinate system you're using could be Cartesian, could be cylindrical, could be spherical. Ultimately, when you're doing the integrals, you'll have to go back to Cartesian. So you should be able to take something which has been defined in spherical and convert it into Cartesian, something which has been defined in cylindrical and convert it back into Cartesian before you can actually do the integrals. Let's do examples, and as we do examples, this will become more and more clear.